Next, let's learn the node voltage analysis. We have introduced the branch current analysis previously. It is a method writing equations in terms of the branch currents and solving the circuits. For a circuit consists of B branches and n-1 independent nodes. When we solve it by using the branch current analysis, there are n-1 KCL equations and B minus n plus 1 KVL equations. The total number of the equations is B, so we can solve the circuit completely. Compared with the 2B method, the equations number of this method has been decreased by half, but for a real circuit, comparing the number of the branches, the independent nodes, and the independent loops, the branches number is still the most. So now we consider how to further reduce the equations number. We all know that for a circuit consisting of n-1 independent nodes, if we can get the voltages of the n-1 independent nodes, since each branch is connected between two nodes, we can get the branch voltages. Then, according to the element constraints, the branch currents can be found. Therefore, our goal is to find such a set of equations in terms of the n-1 independent node voltages. By solving this set of equations, we can get these n-1 independent node voltages. Then the voltages and the currents of all the branches can be determined. In fact, this is a node voltage analysis. Think about how many equations are required for the node voltage analysis. Because we want to find the n-1 independent node voltages, certainly we need n-1 equations. What type of this equation is? Or what is the essence of these equations? We write equations of the n-1 nodes. That is, the sum of the currents flowing into or out of the node is equal to 0. That is, these equations are essentially a set of the KCL equations. Why don't we need to write KVL equations? Unlike the branch current analysis, which needs both the KCL equations and the KVL equations, why does the node voltage analysis only need KCL equations? Okay, let me explain it briefly. According to the uniqueness for the potential in the electrostatic field, we can prove that the KVL equations are satisfied automatically when using the node voltage analysis. Well, let's take this circuit as an example and introduce the steps of the node voltage analysis in detail. The first step, we must select a reference node and label the voltages of the rest n-1 independent nodes. For this circuit, we select the bottom node as a reference node. The rest two nodes are independent, and we label them as UN1 and UN2 respectively. The second step is to write KCL equations for the n-1 independent nodes. Here, it should be emphasized that when writing the KCL equations by using the node voltage analysis, we have special disciplines that the current flowing out of the node are positive and flowing into the node are negative. So for node 1, we have I1 plus I2 plus I3 plus I4 should be equal to the sum of all the current sources flowing into the node on the right, which should be IS1 minus IS2 plus IS3. For node 2, the left part is the sum of all the currents through resistors flowing out of the node. It should be negative I3 minus I4 plus I5. The right part is the sum of all the current sources flowing into the node. It should be IS3 minus IS3. Well, because a node voltage analysis is a method writing equations in terms of the node voltages, so our next task is to express all the currents through resistors with the node voltages. According to the element constraints, we have U1 equals UN1 over R1, I2 equals UN1 over R2. We can also write the expressions for I3, I4, and I5. Substituting these expressions into the KCL equations, we can get these two equations. Sort the two equations, that is, we combine the coefficients of UN1 and UN2 respectively. Finally, we get such a set of equations. This is a standard form of the node voltage equations. We can write it like this. Write the coefficient of UN1 as G11. This coefficient is written as G12. This coefficient is written as G21. And this coefficient is written as G22. The right part is written as ISN1 and ISN2 respectively. Let's see what's the physical implications of these coefficients respectively. First, look at G11. G11 equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. We can see R1, R2, R3, and R4 are all connected to node 1. So the coefficient G11 is actually the sum of all the conductances connected to node 1. For G22, we can see it equals 1 over R3 plus 1 over R4 plus 1 over R5. It also is the sum of all the conductances connected to node 2. We call them the self-conductance of node 1 and node 2. While for G12 and G21, G12 equals minus 1 over R3 plus 1 over R4. It also equals G21 in this circuit. R3 and R4 are connected between node 1 and node 2. So G12 and G21 are actually the sum of all the conductances connected between node 1 and node 2, and a minus sign in the front. We call them the mutual conductance of node 1 and node 2. For the right part, IS1 minus IS2 plus IS3, IS1 flows into, IS2 flows out of, and IS3 flows into node 1. Therefore, ISN1 is the sum of the current sources flowing into node 1. While for ISN2, because IS3 flows out of node 2, so adding a minus also represents the sum of the current sources flowing into node 2. This conclusion can be extended to the circuit consisting of n independent nodes. We write out the standard form of the node voltage equations. It should be a set of equations. In these equations, elements on its main diagonal G11, G22 until Gn are called the self-conductance. The self-conductance is equal to the sum of all the conductances connected to node I. It is always a positive value. For the sentence including voltage source and resistance in series branch, we will explain it in detail in next video. While for the non-diagonal elements G1ij and Gji, we call them the mutual conductance. It is the sum of all the conductances connected between node I and node J. Be sure to add a minus in front of it. It is always a negative value. For a circuit without the dependent sources, the coefficient matrix of the left part should be symmetrical, which means Gij equals Gji. while on the right part, they are the sum of the current sources flowing into each node. Now we have known the physical implications of each coefficient in the node voltage analysis. Hereafter, we need not write the node analysis equations from the very beginning of the KCL equations step by step. According to the physical implications of the coefficients in the standard form, we can write the equations of the node voltage analysis in its standard form directly. It is especially important when solving the complex circuits.